All right, everyone, in this lesson we will take a look at some AP exam questions dealing with related rates. Okay, so let's have some fun here. Number one, a railroad track and a road cross at right angles. An observer stands on the road 70 meters south of the crossing and watches an eastbound train traveling at 60 meters per second. At how many meters per second is the train moving away from the observer 4 seconds after it passes through the intersection? Okay, and this is off an old multiple choice exam. You should be able to tell by the answers that this would have been on the calculator portion, okay? So we can use our calculator here, but obviously there's a lot going on, okay? So let's try to diagram this out. Let's try to label some things we know and notate some of the given information here, okay? So I'm going to draw these two roads. Railroad track and a road cross at a right angle. Observer stands on the road 70 meters south of the crossing. So I'm going to call this the south, the east, north, and the west, okay? So I'm going to label, here's the observer, 70 meters south. They watch an eastbound train traveling at 60 meters per second. And how many meters per second is the train moving away from the observer 4 seconds after it passes through the intersection? So the train's going to be moving in the eastbound direction, and it will have passed the intersection. Okay, so there's my train. Here we go. All right, so at what rate, at how many meters per second is the train moving away from the observer? So here's the observer, here's the train, here's the distance between the train and the observer that will be getting longer as the train continues on to the right. Okay, so let's see. It looks like we're dealing with a right triangle here. 70 is going to be a constant. This side of the triangle is not changing. The top side is, as well as the hypotenuse. So I'm going to use letters A, B, and C to represent the sides of my triangle here. All right. So what do we know? We know that A is a constant, 70. And so therefore we also know that dA dt would be 0 in this case. Okay. That distance is not changing. We know that the train is traveling 60 meters per second. That's a rate of change, okay? That's the rate of change of side B. So we don't know what B actually equals, but we do know the rate of change of side B is that 60 meters per second. And at how many meters per second is the train moving away from the observer? Well, C is the side that represents the distance between the train and the observer, and we want its rate. So we are looking for the value of dC over dt here. All right. Okay, so intuitively, we should be looking at Pythagorean's theorem to get started. A squared plus B squared equals C squared. Taking the derivative with respect to time, 2a to the first times dA over dt plus 2b times dB over dt equals 2c times dC over dt. And while not necessary, I am going to divide both sides by 2 just to make the computations a little easier. All right, so dC dt, there it is off on the right. We're looking for that value. So let's sub in what we know, figure out what we don't know. We need the value of A, that's 70. dA dt is 0. Great. We're going to need the value of B. We don't know it. We'll get that in a moment. dB dt is 60. We're going to need the value of C. And then, once we have B and C, we can sub in and get dC dt. So it still looks like we need two things. We need the value of B. We need the value of C. I think we're going to get B first. Okay. Length of side B. Well, what do we know? We know that the train is traveling at 60 meters per second, and this occurs 4 seconds after it passes through the intersection. So how far would that train have gotten over those 4 seconds? Well, it looks like B is going to be 4 seconds times 60 meters per second for 240 meters in length. Okay, so we can come up with that from the given information. And now we can actually use Pythagorean's theorem at this moment in time to get the hypotenuse C. So 70 squared plus 240 squared equals C squared. And I'll save you the trouble here. It actually comes out pretty nice, 250. Okay, so we get those values. And at this point now, we can grab our calculator and see what we got here. Solve for dc dt. So I'm basically going to do 240 times 60, and then I'll divide that by the 250. And we're getting 57.6 right on the nose, which is choice A. All right, folks. As far as multiple choice related rates question goes, this is a doozy. There's a lot going on here, a lot of responsibility for us to take the words, draw the situation out, do some labeling, do some notating, and then finally solve for what we're looking for, okay? So tough problem, okay? All right, moving on to number 2. And we see angle theta labeled there. In the triangle shown above, if theta increases at a constant rate of 3 radians per minute, at what rate is x increasing in units per minute when x equals 3? So here the angle's increasing. So this angle is going to be presumably getting larger, and x would be increasing as well, going upwards. If theta increases at 3 radians per minute, they're giving us the rate of change of that angle this time. At what rate is x increasing? We want the value of dx dt when x is equal to 3. Okay, so again, we should be thinking SOHCAHTOA. Here's the side with the given rate of change. Here's the side that's presumably a given constant. So we have opposite, and we have hypotenuse here. And so this time we're actually going to use the sine function to set up our trig ratio. Opposite over hypotenuse. So the sine of angle theta is opposite x over hypotenuse 5. And why can I just use the number 5 there? Because again, we're assuming that is a constant. Okay, so again, when we use constants, we can sub the value in right away. So again, to make life as easy as possible when it comes to taking the derivative, I'll write that as 1/5 x. And now, taking the derivative implicitly with respect to t, derivative of sine is going to be cosine theta times d theta dt. The derivative of 1/5 x will be 1/5 dx dt. We're solving for dx. We know d theta is 3. And we need the value of cosine theta here. Well, let's see. This shouldn't be too hard. Opposite over, or excuse me, adjacent over hypotenuse. Well, if this is 3 and the hypotenuse is 5, that's got to be 4, right? So cosine is going to be 4 over 5 here. Okay, and then we'll multiply both sides by 5. And it looks like we get back 12 on the nose for dx dt, 4 times 3 there. All right, folks. So again, kind of a short one, but a trig one. Use the given sides. Okay, notice we didn't set anything up with the 4 initially. We weren't told anything about that side. Okay. Okay, number 3, the radius of a circle is decreasing at a constant rate of 0.1 centimeter per second. In terms of the circumference C, what is the rate of change in the area of the circle in square centimeters per second? Okay, so forget about circumference for right now. What is the rate of change in the area? We want dA over dt, right? And what do we know about area of a circle? Area is pi r squared, okay? So what are we going to do? We're going to take the derivative of this, and let's see what we get. Derivative of the left, dA over dt. On the right, bring down the power, subtract 1, and don't forget dr over dt. Okay. So it looks like we need r and dr to solve this. Now, going back up here, the radius is decreasing at a rate of 0.1 centimeter per second. That's the rate of change of r. That's the value of dr dt here. But notice what it's doing. It's getting smaller. It's decreasing. So dr dt is not going to be 0.1 centimeters per second. It's going to be what kind of 0.1? Hopefully you're thinking negative, okay? So watch out for those little things here. Something's getting smaller, its rate of change is negative. All right, well, I can sub that in for dr now. Now let's worry about this part where they say, in terms of the circumference C. Notice there's a C in all of our answer choices, okay? Well, what is circumference of a circle? Circumference is 2 pi r. So if you think about it, that's exactly what this piece is right here, 2 pi r. So I can replace 2 pi r with the letter c, and we more or less get negative 0.1 c back. And that's choice B up there. Okay, so again, things to look out for. They wanted the rate of change of area. We start with area. We take the derivative of area. Then we worry about this other stuff with the circumference. In terms of the circumference, okay, so I just got to replace 2 pi r with the letter c here. Okay, again, some tricky stuff, but it's meant to be. 4 is particularly tricky. For now, omit this. Once we get through more more lessons on the concept of increasing and decreasing, we'll be able to come back to this problem. But for now, nothing you have to worry about, okay? Give it a try if you want, but do not stress over that one. Number 5, the radius of a circle is increasing at a constant rate of 0.2 meters per second. Okay, so that's going to be what sign? Positive, right? So dr over dt is positive 0.2 meters per second. What is the rate of increase in the area of the circle at the instant when the circumference is 20 pi? Okay, what is the rate of change, rate of increase in the area? So once again, we want the value of dA over dt. So even though there's information about circumference, if we want the rate of change of area, we start by taking the derivative of the area formula. Okay, and now to figure out what dA equals, we need the value of r, and we need dr, which we know is 0.2. So now this is where the information about circumference can help us solve for r. Once again, we know the circumference is 2 pi r, but we also know the circumference equals 20 pi. So I can actually set those to equal, and it looks like the radius is going to be 10 here. Another thing I can do is realize right in dA dt, again, I have this c, that is c. I could actually just replace this whole thing with 20 pi. If you notice, that is indeed what that equals. Okay, so either way, you see that. You can solve for r or just sub in the value of the circumference altogether. Okay, and in any event here, we're going to get back, it looks like 20 times 0.2 would be 4 pi meters squared per second. All right. Again, take your time with these. Pause and rewind as you know you need to. Reach out with any questions you may have. These are the tough versions of these problems for sure. The container has the shape of an open right circular cone as shown in the figure above. The height of the container is 10 centimeters. The diameter at the opening is 10 centimeters. Water in the container is evaporating so that the depth h is changing at a rate of negative 0.3 centimeters per hour. Notice that the rate of change is negative. What's going to happen to the actual amount of water in the cup as the water evaporates? The amount of water is going to go down. Okay. So that makes sense then that the rate of change is negative. In fact, that's our dH over dt here. Part A, find the volume V of water in the container when the height is 5 centimeters. So we actually want the volume of the water here. This isn't too bad. They gave us the formula for volume. So for part A, volume is going to be 1/3 pi r squared h, 1/3 pi, we need r, and the height was 5, okay? Well, this is where you got to try to remember that in every cone, there's a relationship between the radius of the cone and the height of the cone. And in this particular cone, it looks like the height is going to be twice the radius. If the height is 10, the radius was 5 there, okay? Watch out for that. All right, so it looks like the radius is going to be then whatever half the height is. So in this cone, if the height is 5, the radius is going to be 5 halves. And I'm going to write this as 125/12 pi. Okay, that I don't think is going to simplify, so I'll just leave it like that. But there's the volume, okay? And now what we want in part B is find the rate of change of the volume of the water in the container with respect to time, t when h is 5. Okay, so go back to the one we did in the lesson. Look, I can take this initial volume formula, I can go ahead and use the product rule implicitly with respect to t to break this thing up. Then I'm dealing with drdts and dhdts. Look, this problem is really all about dv/dt, the rate of change of volume, and we know what the change in h is. Let's manipulate the original volume formula to take into account for what r equals in this cone. All right, so look, volume we know is 1/3 pi r squared h, but I am going to replace r with 1/2 h here. And if we clean it up, we're looking at 1/12 pi h cubed. So here's the volume of this particular cone. Okay, now if I take the derivative, I've got no more product rule, and I've only got dh's to deal with. So I'm going to get 3/12 or 1/4 pi r squared times dr dt. And we know dh dt, wrong letter, dh dt. Those should be h's, there we go. Okay, 1/4 pi h squared dh dt. And now we know both h and dh. And you know, we could clean this up and punch it in here. So what do we get? 25 negative 75 over 40 pi. And it says indicate units of measure. So the length is in centimeters, but since it's volume, it's going to be what? Cube. So cubic centimeters per hour. And there we have it. Okay, reach out if you have questions on that, or re-watch that cone video in the second lesson. Cone example in the second lesson. Okay, number 7, oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. So that's the rate of change in the volume. The oil slick takes the form of a right circular cylinder, coffee can if you will, where both its radius and height change with time. So it's expanding this way and it's getting bigger, up and down. They gave you the formula, volume equals pi r squared h, okay? At the instant when the radius of the oil slick is 100 centimeters, so r equals 100 centimeters, the height is 1/2 centimeter, the radius is increasing at a rate of 2.5 centimeters per minute. So that's the value of dr dt. At this instant, what is the rate of change of the height of the oil slick? So what are we after? dh dt with respect to time in centimeters per minute. Okay, so here's our volume formula. Volume, radius, and height are both changing here, so neither of these are constants. It's not like a cone where we're going to find one in terms of the other here, okay? We're going to have to use the product rule to take the derivative of this. So taking the derivative, on the left we get dv dt. On the right, the derivative of pi r squared, 2 pi r to the first times dr dt times the h. Plus, keep the pi r squared times the derivative of h with respect to t. And there is our derivative. And if we now want to solve for dh, we got to know everything else. And I think we do here. dv, they told us, was the constant 2,000. R is 100. dr, 2.5. H, 0.5. R, 100. And then dh is what we're looking for. And at this point, I would just use a calculator. Okay, I'm going to do 2,000, and I'm actually going to end up subtracting this quantity away. So 2,000 minus this weird-looking value here. And then I'm going to divide by the 100 squared pi. And I am getting about 0.039 centimeters per minute for the change in height. The height is growing much more slowly than the radius is. It's spreading outward much more quickly than it's spreading up and downward. That's what that tells me. Okay, but there's your value. Okay, a couple to go. Another cylinder one, but with a big difference here, okay, than the last one. Coffee pot has the shape of a cylinder with a radius of 5 inches as shown in the figure above. Let h be the depth of the coffee in the pot measured in inches, where h is a function of time t measured in seconds. The volume V of the coffee in the pot is changing at a rate of negative 5 pi radical h cubic inches per second. So what does that represent? The change in volume. So dV dt is that negative 5 pi radical h. Okay, cubic inches per second. They've reminded us of the volume formula again, and now they want us to show that the rate of change of the height with respect to time is negative radical h over 5. So they're basically telling you, here's the answer, show us how to get to that, okay? Well, here's the big difference between this cylinder and the previous one. Is the radius of this cylinder changing as the volume of coffee goes up or down? No. So here, the radius is a constant. So when I go to take the derivative of this volume formula, I don't have to use the product rule. Since r is a constant, I can sub it into this formula right away. So watch, volume pi r squared h, but r is a constant 5. So what's that going to give us? 25 pi h. Right, 5 squared was 25. Now there's no more product rule and a pretty easy, straightforward derivative as far as this stuff's concerned. So on the left, 1 dV over dt. On the right, 25 pi times dH over dt. We know what dV dt is. That was given to us. We had to make sense out of that, sub it in. And now do a little division. And sure enough, when we simplify this, we get negative radical h over 5, just as we were supposed to show. Okay, so you got to go through the work to show that end result, and there it is. Okay. So again, watch those constants. If something's a constant, you can make life a lot easier by subbing it in right away. If it's not a constant, you can't do that. And number 9. Ship A is traveling due west toward Lighthouse Rock at a speed of 15 kilometers per hour. So that's ship A. We're going toward Lighthouse Rock, and so we got that, okay? At a speed of 15 kilometers per hour. So that's side X. What's happening to the length of side X here? Is it getting bigger or smaller? It's getting smaller. So dx dt, negative 15 kilometers per hour, okay? Watch those negatives. Ship B is traveling due north away from Lighthouse Rock. So that looks like this at a speed of 10 kilometers per hour. That's the rate of change of side Y. Since that distance is increasing, the rate of change will be positive 10 kilometers per hour. Let X be the distance between ship A and Lighthouse Rock at time t. Let Y be the distance between ship B and Lighthouse Rock at time t as shown in the figure. Okay. Find the distance in kilometers between ship A and ship B when X is 4, Y is 3. All right, I'm going to call this side Z. You probably don't have to work too hard for that. What's it going to be, folks? 5, right? We got a 3, 4, 5 right triangle. Part B, find the rate of change in kilometers per hour of the distance between the two ships when X is 4 and Y is 3. Okay, so I'm calling side Z the distance between the ships. We want the rate of change of that, so we want dz over dt here. Okay, well, we do have a right triangle, so that'll relate our sides. Taking the derivative with respect to t. And again, I'm just a fan of simplifying as I go. And let's see, sub in we know. So x is 4, dx negative 15, y is 3, dy is 10, z is 5, and we're looking for dz dt. And dividing, it looks like we get negative 6 kilometers per hour is the rate of change and the distance between the two ships at this moment in time, right? And what does that mean? What does that say about the distance between the two ships? They're actually getting a little bit closer together. The rate of change of side Z was negative, so the length of side Z, the length of that hypotenuse at that moment, is getting shorter. And then last up, part C. Let theta be the angle shown in the diagram. It's over here. Find the rate of change of theta in radians per hour when x is 4 and y is 3. Now, I've been saying find the sides with the given rate of change and the given constant. Well, side y was a given rate of change. Side x was a given rate of change. There was no side with a given constant here, okay? So we have to use the original sides, x and y. And let's take a look at this here. So let's see, trig-wise, we have opposite and adjacent. So we're looking at tangent of theta equals opposite over adjacent. Now again, it would be convenient to be able to sub a 3 or a 4 in for y or x, but we can't. Nothing is a constant here. So we're going to have to use the quotient rule to take the derivative this time. There's no way around it, okay? So going through, the derivative of tan theta will be secant squared theta times d theta dt. On the right-hand side, the derivative of the top will be dy over dt times the bottom minus the derivative of the bottom, dx over dt times the top over bottom squared. All right, and so now we need the value of secant squared theta, and we need to sub in what we know about these other values. dy was 10, x was 4, dx negative 15, y 3, x 4. Secant squared theta. Here it's pretty easy to get the cosine value. Cosine of our angle adjacent over hypotenuse would be 4/5. So the secant value is 5/4, and if I square that, we get 25/16. Okay, and now from here, let's see if we can clean this up a little bit. 40 plus 45 is 85 over 16. I'll multiply both sides by 16. Just gets rid of those. And then I'll divide by 25. And always in radians per unit of time. Okay, you don't need to simplify that. You can if you want. I believe that would be 13/5, but that's not necessary. Okay, or 17/5, excuse me. All right, folks, but there you go. A bunch of AP exam related rate problems. Hopefully you got a better sense of how these work. You can practice them a bunch if you really need to, so that if you see one on your exam, you'll be ready to go.